We all turn on the tap, right? And we expect clean, fresh water to just be there. It's almost like magic.
Right.
But have you ever stopped to think about the really complex stuff happening behind the scenes? Like the waste created just making that water safe. Today on the Deep Dive, we're pulling back the curtain on something called multitasking, finished water and residuals.
Yeah, residuals, basically the byproducts, the leftovers, the stuff that gets generated when we're making sure our drinking water is absolutely pristine.
Exactly. And our mission today is really to unpack what these residuals are. Why are they so critical? Not just for, the smooth running of a water treatment plant, but really for everything, their budget, environmental sustainability. We want to give you a kind of shortcut to understanding this, often invisible but very highly regulated part of getting clean drinking water to your home.
Yeah, sure, shortcut sounds good. And for many of you listening, especially if you're interested in the practical side of things, how vital infrastructure works. Understanding these byproducts gives you some real aha moments, particularly for those medium-sized plants. It shows where the hidden costs and complexities really are.
Okay, so let's unpack this then. Residuals, it sounds a bit, I don't know, vague, like leftover dinner or something.
Yeah.
What exactly are they in this context?
Yeah, it sounds vague, but believe me, to a plant operator, it's anything but. In drinking water treatment, residuals are simply the byproducts, the waste streams generated when you take raw water, from river or lake and treat it to meet those really strict finished water standards. Think of it as everything that was in the raw water originally, plus some of the treatment chemicals maybe that we definitely don't want ending up in your drinking glass.
Okay, so what kind of stuff are we talking about? Give me some examples.
Sure. Well, the big one is usually sludge. That's the concentrated solids you get when chemicals, coagulants, make tiny particles clump together and settle out.
Right, the gunk.
Pretty much, yeah. Then there's filter backwash water. That's literally the water used to clean the filters, carrying away all the trapped stuff, the turbidity.
Makes sense.
You might also get concentrate or brine if the plant uses special processes like membrane filtration or softening, and sometimes even trace amounts of chemical residuals from the treatment itself.
So it's not just a tiny bit of material. It's quite a stream of different byproducts. Why do they matter so much? Is it just about getting rid of them?
Oh, it's way more than just disposal. It's really multifaceted. First off, there's regulatory compliance. Big agencies like the EPA, the Environmental Protection Agency, and state ones like Virginia, DEQ, Department of Environmental Quality, they have strict rules.
Strict how?
Strict about how residuals are handled, how they're stored, how they're ultimately disposed of. If you want to discharge the liquids into a river or put the solids on land, you almost always need specific permits, and you have to meet really tight standards. Getting it wrong, not an option. Serious consequences.
And here's something that really jumped out at me. The cost. I saw this stat, and it seems kind of shocking. Residuals disposal can be something like 30 to 50% of the operating costs in medium-sized plants.
That's right.
We're talking plants treating, 10 to 20 million gallons a day, MGD?
Yeah, roughly that size.
That's a massive chunk of the budget. Sometimes like 15 to 25% of the total O&M costs. And unlike the chemicals they add to treat the water, these costs don't directly make the water cleaner, right? They're just the cost of doing business.
That's exactly it. And beyond the money and the rules, there's the environmental and community impact. If a plant can reduce how much sludge it produces, that means fewer trucks hauling it away.
Less traffic, less fuel burned.
Exactly.
Right.
Less landfill space used up. And if they can minimize brine from, say, membrane treatment, that's huge for sustainability, especially in places where water is scarce.
Right.
Every drop counts there.
You mentioned that 10-20 MGD plant size.
Yeah.
Why is that range particularly interesting or challenging?
It's a real sweet spot, or maybe a tough spot, depending on how you look at it. These plants are big enough that residuals are a significant cost and a complex problem to manage, but they're often not quite big enough to justify the huge multi-million-dollar super advanced solutions that a really large facility, say 100 MGD or more, might invest in.
Okay. So they're kind of caught in the middle.
Precisely. They're constantly performing this balancing act. They have regulatory pressures pushing them, costs they need to control, and a range of technology options. Maybe lagoons for storage, maybe mechanical dewatering, maybe hauling it off-site, maybe even recycling some streams back into the plant. What's interesting is, if they get it right, optimizing residuals isn't just about managing waste better. It can actually give them more operational flexibility throughout the plant and even help their main equipment last longer.
So the big takeaway here is residuals are just part of the deal. They're unavoidable. But how a plant handles them, That directly hits their wallet, their compliance record, and their environmental footprint.
Couldn't have said it better myself.
All right, let's try and visualize this. Let's take a virtual walk step by step through a typical plant in that 10-20 MGD range. I want to pinpoint exactly where these residuals, this waste, actually gets generated.
Great idea. Let's follow the water.
Okay, step one, raw water intake. Water comes in from the river, lake, whatever.
And boom, right away you've got residuals, screenings and debris, things like sticks, leaves, algae, maybe some trash. That stuff gets screened out and usually just goes to a landfill. Sometimes grit removal happens here too. That sand goes off for disposal.
Okay, screens take out the big stuff, then the water goes to rapid mix and coagulation. That's where they add chemicals, right?
Yeah, chemicals get dispersed really quickly to destabilize the tiny particles floating in the water. At this stage, you're not generating a big continuous waste stream. It's more like the precursors to the sludge are forming. Mostly the waste here is just empty chemical containers.
Gotcha. Next up, flocculation and sedimentation. Gentle mixing. Particles clump up into bigger bits called flock, and then they settle out.
Bingo. This is a major waste point. Huge one. All that settled stuff is settled sludge. It's a mix of the treatment chemicals, usually metal hydroxides like alum or iron, plus all the solids they've captured from the raw water.
And what happens to that sludge?
Typically, it's withdrawn from the bottom of the tank, then it often goes through thickening, then dewatering to squeeze out more water, creating a semi-solid cake. That cake is the final product that gets hauled away, landfill, or maybe land application, which we can talk about later.
Okay, what about the water that's left after the sludge settles?
Good quote. The liquids separated during thickening and dewatering, often called filtrate or centrate, are usually recycled back to the start of the plant, the headworks, or sometimes discharged to the sewer system, but only if they have a permit for that.
All right, sludge handled. What's next for the water?
Filtration. This step polishes the water, removing any tiny particles that didn't settle out, getting rid of that cloudiness or turbidity. Filters might be sand, anthracite coal, granular activated carbon, GAC, or even membranes.
And filtration must create waste too.
Oh yeah, another major residual source. When those filters get dirty, they have to be cleaned. That cleaning process is called backwashing. So you get filter backwash water, which is full of the solids rinsed off the filters. There's also usually a filter to waste step right after backwashing.
Okay, so more dirty water. Where does that go?
Typically, the backwash water goes into an equalization tank to let the solids settle out again. The clearer water on top, the supernatant, might be recycled back into the plant or maybe discharged to the sewer. And the settled solids, they usually get combined with that main sludge stream from sedimentation.
Makes sense to combine them.
Yeah, keep it together. And if the plant uses membrane filters, you'd also have a concentrated reject water stream to deal with, which can be tricky. Plus, periodically, the filter media itself, sand, GAC, needs replacing. That spent media is another residual.
Wow, okay. So after filtration, the water's pretty clean.
Getting there. Now it's into the clear water stage. Disinfection happens here, usually with chlorine. Then the water sits in tanks for contact time and storage. Then it's pumped out via the finished water pumps into the distribution system, the pipes leading to homes and businesses.
Do these last stages generate much waste?
Not continuously, no. Very minimal in normal operation. You might have occasional tank drain downs for cleaning or water flushed from the distribution mains. That water needs to be dechlorinated before it's discharged, usually to the storm drain or sanitary sewer. And again, empty chemical containers from disinfection.
So just to recap the big ones, the main sources of continuous significant residuals volume are really that sludge from sedimentation and the filter backwash water.
You got it. Those are the two heavyweights in terms of volume and management effort in a conventional plant.
Okay, it's becoming really clear just how much water operators have on their plates. Their main job, obviously, is ensuring the water coming out is safe to drink, meeting all those standards. But what else are they juggling day to day, especially related to these residuals we've been talking about?
Their responsibilities are incredibly broad, you're right. On the finished water side, yes, meeting standards is paramount. They're constantly monitoring the process, often using sophisticated SCADA systems that supervisory control and data acquisition. They do physical walkthroughs of the facility, lots of sampling and lab work, meticulous operations logging.
Supply chain stuff too, I imagine. Ordering chemicals.
Absolutely. Managing supplies, responding to alarms 24/7. It's a huge job. But then layered right on top of all that are these very specific, often kind of hidden tasks directly tied to managing the residuals.
Ah, okay. Like what?
Well, for instance, polymer management. We mentioned polymers help dewatering. Operators have to optimize the dose not too much, not too little, for the thickening and dewatering equipment to work efficiently. That takes skill.
Right.
They're also directly operating the thickening and dewatering equipment itself, running the gravity thickeners, belt presses, centrifuges, whatever the plant has. That's hands-on work.
And the permits.
Critically important. They're responsible for VPAN PDE's compliance. VPA is Virginia Pollution Abatement. NPDES is the National Pollutant Discharge Elimination System. This means collecting specific samples from the residual streams, getting them analyzed, and reporting the results, things like TSS, total suspended solids, percent solids in the sludge cake, pH, sometimes metals.
So lots of sampling and paperwork just for the waste side.
You bet. And finally, there's the logistics. Truck loading and receiving, coordinating with the sludge haulers, making sure trucks are loaded correctly, maybe weighing them, verifying load tickets. It all falls under their purview.
So really, what does this all mean for the person doing the job? It sounds like water operators are performing this tightrope walk every single day. They're the frontline guardians of public health, focusing on that perfect finished water quality. And they're also the back-end waste managers, dealing with the nitty-gritty of handling these complex, messy residuals. That's a pretty demanding dual role, isn't it?
Yeah. It absolutely is, and you can't neglect either side. If finished water quality slips, public health is at risk. If residuals aren't managed properly, you risk compliance violations, soaring costs, equipment damage, and ultimately losing public trust. It requires a really diverse skill set and constant vigilance.
Okay, let's dig into those costs a bit more. We know residuals can be expensive. What are the key factors that really drive up the budget for managing them? What makes the needle move on cost?
Good question. There are several key drivers. First, as we touched on, are the permit requirements. What pollutants does the permit limit? Solids, metals, nutrients. How low are those limits? How often do they need to sample? Stricter permits almost always mean higher treatment and handling costs to meet those limits consistently. Second is the thickening process. How does the plant reduce the water content in the sludge before final dewatering or disposal? They might use gravity thickeners, dissolved air flotation, DAF, or gravity belt thickeners.
And the benefit there is less water to haul away, right?
Yeah. Exactly. Lower hauling volume means fewer trucks, lower transport costs. And thickened sludge can sometimes be more stable. But the flip side is the cost of that thickening equipment, the energy it uses, and often more polymer chemicals.
And sludge doesn't just appear conveniently between 9 and 5. How does timing factor in?
Right, that leads to operating hours. The equipment for handling sludge thickeners, dewatering units, pumps often runs on a different schedule than the main water treatment process. Maybe it only runs one shift, or maybe it has to run 24/7.
Okay.
Longer operating hours mean higher energy costs, higher labor costs if operators need to be there specifically for residuals. Plants have to balance the continuous production of sludge with their staffing schedules and energy use.
What about getting it off-site?
That brings in truck loading and storage. Key cost factors here are: how often do trucks need to come? What's the frequency? How much storage capacity does the plant have on-site? Do they use lagoons, silos, roll-off dumpsters? Limited storage means trucks have to come more often, maybe even on weekends or nights at higher rates. And weather can shut down hauling, so storage provides a buffer.
You mentioned polymers before as being crucial but expensive.
Yep, polymer systems are a major one. Polymers are essential for making thickening and dewatering work well, but they are a significant chemical cost. Getting the dose wrong, especially overdosing, is just throwing money away, and it can actually gum up the equipment. So optimizing polymer use is a huge lever for controlling residuals costs.
Okay, and finally, the big machinery itself, the dewatering part.
Exactly. The dewatering technology is core. This is the step that turns liquid sludge into a manageable, crumbly cake, usually aiming for 15–30% solids. The main choices, as we'll discuss, are usually belt filter presses, centrifuges, or screw presses. Each has different upfront capital costs, energy demands, labor needs, maintenance requirements, and they achieve different levels of final dryness, which impacts hauling costs.
So it really sounds like when a facility manager says residuals are 20% of my O&M budget, what they're really saying is, all this sludge handling, the thickening, the dewatering, the polymer, the hauling, that's the hidden, expensive half of my operation. It's not the glamorous part maybe, but it's where efficiency can make or break the budget.
In perfect summary, it's absolutely critical.
Which leads nicely into thinking about investment. If it's such a big cost center, there must be ways to invest smartly to bring those costs down. We're talking return on investment or ROI.
Precisely. Residuals management isn't optional. You have to do it. But how you do it offers strategic choices. ROI in this context is usually about spending capital money up front, maybe on automation, better storage, more efficient dewatering equipment to achieve bigger savings in the long run.
Like saving on labor or hauling or chemicals.
Exactly. You calculate the payback, divide the upfront capital cost by the annual savings. For example, if you spend, say, $1.5 million on a new centrifuge, but it cuts your annual hauling and polymer costs by $300,000. Well, that's roughly a 5-year payback. After year 5, those savings go straight to the bottom line.
Makes sense. You also mentioned operating hours. How does that play into ROI?
Well, operating hours and shift schedules tie into staffing and storage. Some plants might choose to process residuals only during, say, the day shift. This might require investing in larger storage capacity to hold the sludge generated overnight and on weekends. The potential ROI there is lower labor costs.
Versus running 20/47.
Right. Running 24/7 might require less storage investment, but could mean higher continuous labor and energy cost. The best model depends on the plant's specific flow rates, how much sludge they produce, their storage options, and their staffing setup.
Automation seems like it would be a huge lever here for improving efficiency and getting that ROI.
It really is. Automation can pay back quickly by reducing labor needs and improving consistency. Think about instrumentation. Online solids analyzers that can automatically adjust the polymer dose in real time, preventing waste.
Or cameras.
Yeah, cameras providing visuals inside tanks or on conveyor belts, monitoring sludge blanket levels or cake dryness. This takes the guesswork out for operators. And integrating all this with the plant's main control system, the SCADA or PLCs, programmable logic controllers, allows for automated pump speeds, chemical feed rates, alarm notifications.
So less manual tweaking, fewer errors.
Definitely. Less operator time spent babysitting the residuals process, less chemical waste, less equipment downtime. Paybacks for automation projects and residuals can often be in the 2 to 4 year range, which is pretty attractive.
What about storage? You mentioned silos, dumpsters. How does investing there provide ROI?
Good on-site storage provides crucial operational flexibility. Silos are common for dewatered cake. They offer enclosed storage, which helps with odor control, and allow plants to load trucks on a more predictable schedule, maybe just during regular business hours.
Compared to just like a pile on the floor.
Right, or open dumpsters or roll-offs. Those have lower capital costs but might require more frequent hauling, are exposed to weather, and might have odor issues. Floor storage is flexible but has safety and housekeeping considerations. The ROI from better storage comes from avoiding expensive emergency or off-hours hauling, being able to better match the hauler's schedule, and reducing operator overtime spent waiting for or loading trucks.
So stepping back, optimizing residuals management through these kinds of investments, automation, storage, efficient equipment, is really about transforming what can be a reactive, unpredictable, labor-intensive process into something much more controlled, predictable, cost-efficient, and flexible.
That's the goal. It's shifting from constantly reacting to problems to proactively managing the process, and the financial benefits follow.
Okay, let's get into the nitty-gritty of the machines themselves, the ones that actually squeeze the water out of the sludge. What are the main dewatering technologies we typically see in these medium-sized plants?
Sure. The 3 workhorses you'll most often encounter are centrifuges, screw presses, and the older standby belt filter presses. Let's start with the centrifuge. You can think of it as a kind of industrial-scale salad spinner, maybe.
Why?
It's a rotating drum that spins the sludge at really high speeds. The centrifugal force separates the heavier solids from the lighter water.
What are the pros and cons?
Well, the big advantages of centrifuges are usually high solids capture. They can often produce a drier cake, say 18 to 30% solids, which means less weight to haul. They're also fully enclosed, which is great for minimizing odors. They can run continuously and be highly automated.
Sounds good. Downsides.
The main ones are high upfront capital cost. They're expensive machines and high energy consumption because they spin so fast. Maintenance can also be complex and require specialized skills, and sometimes the high-speed shearing action can break up the flock particles a bit.
Okay, high performance, high cost. What about the screw press? That sounds gentler.
It is. The screw press works quite differently. It uses a very slow-moving screw inside a cylindrical screen. As the sludge moves along the screw, the channel gradually narrows, gently squeezing the water out through the screen.
And the advantage is there.
Lower energy use is a big one, much lower than centrifuges. They're also quieter, generally simpler mechanically, easy to automate, and often require less maintenance. They can also tolerate varying flows pretty well. It's a technology that's really gained popularity, especially for small to medium plants.
Disadvantages.
Typically, they produce a slightly wetter cake than a centrifuge, maybe in the 15 to 25% solids range. They can also have a larger physical footprint for the same processing capacity. And being a bit newer than centrifuges or belt presses, there might be fewer operators with long-term experience on them, though that's changing fast. They can also be slower in terms of throughput.
Okay, gentle, but maybe not as dry. What about the old reliable, the belt filter press?
Ah, yes, the belt filter press, or BFP. These have been around a long time. The basic idea is you mix the sludge with polymer, then spread it onto porous belts. These belts then travel around a series of rollers that squeeze the sludge sandwich, forcing water out through the belts.
Pros and cons of the BFP.
Advantages include a moderate capital cost compared to centrifuges. It's a very proven and reliable technology, and it produces a reasonably dry cake, again, often 15 to 25% solids. A key thing operators often like is that it's visual. You can actually see the sludge being dewatered and make adjustments on the fly. The downsides. BFPs tend to be more labor-intensive. They require a lot of operator attention for monitoring, and especially cleaning those belts need frequent watching. Because they're open, they can have issues with odors and splashing, making housekeeping important. They also often require relatively high polymer doses to work effectively, and the belts themselves are wear items that need periodic replacement.
So, three main options, each with its own trade-offs in cost, performance, operations.
Exactly. The best choice really depends on the plant's specific sludge characteristics, their budget, staffing levels, energy costs, and disposal requirements.
Now, you've mentioned polymers multiple times as being absolutely essential for making these dewatering machines work well. Can you explain a bit more what exactly are polymers in this context?
Sure. Think of polymers as molecular glue, or nets. They are very long-chain chemical molecules that, when added to the sludge, help bind the tiny solid particles together. They create larger, stronger clumps called flocks.
Why is that important?
Because those small individual sludge particles hold onto water really tightly. By forming larger flocks, the polymer makes it much easier for the mechanical equipment, the centrifuge, screw press, or BFP, to separate the water from the solids. Without effective polymer conditioning, the sludge would stay watery, and dewatering would be inefficient or maybe wouldn't work at all.
Okay, so they're critical. Are there different kinds?
Primarily, yes. You generally choose between dry polymer and liquid polymer, which is often an emulsion. Dry polymer comes as a powder or granule. Its main advantage is it's usually cheaper on a per pound of active polymer basis, and it has a longer shelf life.
Yeah.
But it requires more complex equipment to handle and make down, meaning dissolve it properly in water. This takes time, often 30 to 60 minutes of mixing and aging for hydration. And there's a dust hazard operators need to manage carefully.
And liquid polymer.
Liquid polymer emulsion comes as a thick liquid. It's generally much easier to handle and use. The make-down systems are simpler, it requires less prep time, you can use smaller tanks, and you can adjust the dose much faster. The downside is it's typically more expensive per unit of active polymer, and it has a shorter shelf life, maybe 6 months to a year, depending on the product and storage conditions.
So again, trade-offs based on cost, convenience, space.
Exactly. And storage is key too. Plants need properly sized day tanks, make down tanks, mixing tanks usually made of corrosion-resistant materials like plastic or stainless steel to ensure they don't run out and that the polymer is prepared correctly.
How do operators figure out the right polymer and the right dose? Is it just trial and error?
Not ideally. That's where bench testing comes in. It's often called jar testing when applied to sludge. It's a small-scale laboratory test where operators take sludge samples and mix them with small, measured amounts of different polymer types and doses.
What are they looking for?
They observe things like how quickly the flocks form, how large and strong they look, how quickly the solids settle out, and sometimes they'll even try to simulate dewatering on a small scale, like squeezing the sample in a filter paper to see how clear the released water filtrate is and estimate cake dryness. It's a relatively quick and inexpensive way to troubleshoot problems or screen new polymers before trying them full scale. Saves a lot of chemical costs, potentially.
Okay, so bench tests help dial in the chemistry. But what if a plant is thinking about buying a whole new dewatering machine, like switching from a BFP to a screw press? That's a huge investment.
Absolutely. You wouldn't rely just on a jar test for that. That's where pilot testing becomes invaluable. This usually involves renting a mobile, trailer-mounted version of the equipment they're considering, like a pilot centrifuge or a pilot screw press.
So they bring it right to the plant?
Yep. They hook it up to the plant's actual sludge feed for a period, maybe a few weeks or even months. This gives them real-world, site-specific data on how that technology performs with their sludge. They can measure actual cake solids, polymer consumption, energy use, filtrate quality, and importantly, get operator feedback on how easy or difficult it is to run and maintain.
That sounds crucial for justifying a big capital expense.
It is. That pilot data is often essential for building the business case, securing funding, and ensuring they're making the right long-term investment.
Okay, let's shift gears slightly and talk about one specific disposal option that comes up, especially with certain types of residuals. Land application. What exactly does that involve?
Land application in this context means taking the dewatered water treatment residuals, or WTRs, specifically those resulting from using aluminum or iron salts as coagulants, and spreading them on permitted agricultural fields or sometimes land reclamation sites. In Virginia, this process is typically regulated under Virginia Pollution Abatement, or VPA, permits.
Why would a plant do this instead of landfilling?
The main driver is often the chemical properties of those alum or iron residuals. They have a very strong capacity to bind with phosphorus. So, applying them to soils, particularly agricultural soils that might have high phosphorus levels, can help lock up that phosphorus and reduce the amount that runs off into waterways, where it can cause environmental problems like algae blooms. It's seen as a form of beneficial reuse.
Interesting. But it sounds logistically complex. What are the costs involved?
The costs and logistics can indeed be significant. Key cost drivers include how dry the cake is, percent solids, because that dictates hauling weight, the hauling distance to the application fields, the permitted application rate, how many tons per acre, field accessibility, which can be seasonal or weather dependent, and of course, the costs of compliance sampling and analysis.
And managing the trucks must be a big part of it.
Huge. Efficient trucking and loadout is critical. Many plants invest in on-site truck scales. This helps avoid overweight fines for the haulers, accurately verifies the tonnage being shipped for billing and reporting, helps optimize truck loading, and speeds up the driver turnaround time. If haulers are paid per load, keeping them moving efficiently is important, and it reduces how much time plant operators have to spend babysitting the loading process.
What about storage for land application?
Storage and handling choices impact cost and labor significantly. Silos with automated conveyors offer the highest capital cost but generally lowest labor, best odor control, and buffer capacity. Using roll-off containers or designated floor bins is lower capital, but usually means higher labor for loading moving bins and more exposure to weather. Lagoons are sometimes used for liquid sludge storage prior to dewatering for land application, very low capital but high footprint, potential odors, and labor-intensive cleanouts. These choices directly affect staffing needs.
Now, a really big and frankly worrying topic these days is PFAS. How does that factor into land application of water treatment residuals?
That is the critical emerging issue, yes. PFAS, per, and polyfluoroalkyl substances are a group of persistent human-made chemicals. The EPA issued interim guidance in 2024 specifically looking at managing PFAS-containing residuals, particularly things like spent granular activated carbon, GAC, used to remove PFAS from water, or concentrate from membrane systems treating PFAS-impacted water.
So does it directly impact the alum or iron sludge?
It can, indirectly or potentially directly, depending on the source water and treatment. If a WTR stream might be commingled or co-handled with known PFAS-bearing media, it's going to face much closer scrutiny under that guidance. More broadly, though, the EPA is also finalizing risk assessments for PFAS compounds like PFOA and PFOS in biosolids, sewage sludge, intended for land application, expected around 2025.
And that's spilling over.
It absolutely is. Those findings and the surrounding public discussion are shaping state policies and public perception regarding any material being land applied, including WTRs. We're already seeing significantly increased scrutiny, testing requirements, and costs, sometimes dramatically higher costs per wet ton for land application programs in states implementing PFAS restrictions. Plants absolutely need to plan conservatively and stay on top of evolving guidance.
So if a plant in Virginia, for example, wants to pursue or continue land application, what's the path forward look like, especially under VDEQ?
The pathway is through that VPA permit. It involves detailed site assessments, nutrient management plans for the fields, establishing buffer zones, meeting limits for metals and other parameters in the residuals in soil, and rigorous record keeping. The specifics can vary, so plants must always adhere to their current active permit language, and they need to be proactively discussing PDS with VDEQ to understand current or anticipated requirements.
Given all that complexity, especially PFAS, what's the operational playbook for making land application work reliably for, say, a 1020 MGD plant?
Okay, a practical playbook would look something like this. 1. Characterize and test first. Do thorough bench or pilot testing for dewatering performance. Critically, conduct PFAS screening if there's any reason to suspect it might be present. Discuss testing protocols with DEQ and align with EPA guidance. Know your residuals inside and out before you plan application. 2. Engineer for reliability. Invest in automation where it makes sense. Polymer systems, conveyor interlocks, absolutely install truck scales and implement standard operating procedures, SOPs for weighing tear gross, tracking load tickets, and monitoring driver turn time as a key performance indicator, KPI. Right-size your storage to provide a buffer for bad weather or trucking delays. 3. Permit alignment is key. Know your VPA permit conditions cold. Understand soil monitoring needs, agronomic rate limits, seasonal restrictions, buffer zone requirements, metals testing frequency, and any current or pending PFAS language. Keep impeccable logs documentation as your best friend during inspections. 4. Field execution and maintenance. Have solid QA/QC procedures for your hauling and application contractor. Actively manage potential odors. Have contingency plans. What's your backup disposal option if fields are too wet for weeks? Do you have critical spare parts for your dewatering and loading equipment?
That's a comprehensive list. So, weighing it all up, pros and cons.
Pros. Potential for beneficial reuse, particularly phosphorus binding. It can be a lower disposal cost compared to some landfill options, and it can contribute to a positive public image around sustainability if managed transparently and effectively.
The regulatory landscape, especially PFAS, is complex and rapidly evolving. Major weather or seasonal access limitations can create storage and scheduling nightmares, and community perception is fragile. Negative headlines about PFAS, even if unrelated to WTRs, can create opposition.
So the bottom line for that medium-sized plant considering this route.
The bottom line is, prove your chemistry first. Bench pilot tests, including PFAS. Engineer robust systems, automation, scales, storage to minimize labor risks and hauling disruptions. And work closely with DEQ to ensure a clear, defensible VPA permit path, keeping a very close eye on PFAS developments. If you do it right meticulously, it can be cost-effective and environmentally sound. But if you approach it casually, it can easily spiral into a major staffing, compliance, and PR headache.
Wow. This deep dive has really peeled back the layers on something most of us never think about. The sheer complexity and the hidden challenges of managing residuals in drinking water treatment. It really is this invisible ballet happening constantly behind the scenes. It's not just about the clean water from the tap, it's about responsibly handling everything left over.
It truly is. So maybe next time you turn on the tap, take a second to consider that complex dance, the chemistry, the mechanics, the regulations, the dedicated operators, all working together not just to make your water safe, but also to manage these byproducts responsibly and sustainably. This deep dive really shows that protecting public health goes way beyond just cleaning the water. It's about smartly managing everything that's left behind. And maybe a final thought to leave you with. What other hidden, complex processes underpin our daily lives, impacting our environment and our budgets that we rarely, if ever, stop to consider?